Okay, now we are all in. So it's a pleasure for me to have Laura Rodríguez today with us. Actually, it's a lot of time already that we tried to invite you to come, but I don't know why. Maybe because we are so close, because she's working at the University of Barcelona, that it took a while to find the moment. But today is the moment to have you here. I think that your expertise can have synergies with different research lines of our centers. So I'm happy to see a lot of people today here to listen to you. Let's say a few words about your trajectory. So Laura Rodríguez completed her PhD in chemistry at the Universitat of Barcelona in 2003, working on metallic clusters and supramolecular chemistry. Then she has done a postdoc in Portugal in Universidade Nova de Lisboa, and there she acquired very strong background and expertise in photophysics. After the postdoc, she returned to Universitat de Barcelona as a faculty member in 2008, and then in 2020 became full professor there at the Universitat of Barcelona. She's leading the group of Supra and Nanostructured Systems at the Faculty of Chemistry. Her research interests combine molecular design, self-assembly, and photophysics. And specifically, I think that here is also, you have a lot of expertise working with gold and platinum complexes. And she mainly used three tools for her work, that is organometallic chemistry, supramolecular assemblies, and luminescence towards functional materials. She has published more than 140 papers and led several national and European research projects, as well as collaboration with companies. Actually now, currently, she's the coordinator of a cost action that is called LUCES, related to supramolecular luminescence and sensing, in which our group actually is also involved, and this is the thing that activates a bit this invitation. And is an active member also of several national and European networks. So finally, I would like to say that I'm very, very proud. Maybe that's why we wait a little bit to invite you, that very recently she has been awarded the Premio de Excelencia Investigadora del Grupo Especializado de Química Organometálica de la Real Societat Española de Química. So congratulations for this deserved award. And yes, we are happy that you are here right after this. So that's a bit what I wanted to say. So now the floor is yours, Laura.
Okay, thank you, Ima, for the kind introduction. And I'm also very happy to be here in my first time here at the ICMAB, although we are very close, but it seems that it's not so easy to take the car as we have friends here saying, oh, it's so difficult to come to the UAB. Yes, it seems that it is difficult because the day by day it's, well, difficult in all this, just moving a little bit from our place. As Ima said, we work with supramolecular chemistry, but well, we are mainly focused at the Faculty of Chemistry at the University of Barcelona. I don't know if you know it, but well, we are at the second floor in Organic Chemistry department, and this is the group that I am leading, Supra and Nanostructured Systems. Well, this was the picture of last year, but it should be updated with new people that has entered and some others that left. Okay, so our main expertise and research interests are those here presented. So we work with supramolecular assemblies with different types of applications, mainly on luminescent materials, mainly on room temperature phosphorescence, also singlet oxygen production, and also on sensing, all of them using supramolecular chemistry and luminescence. Okay, as part of the inorganic chemistry department, we like metals also, apart from organic chemistry, but as Ima said, in the recent years, we have been more focused on platinum and gold. And the examples that I will show you today are based on these gold and platinum systems. Okay, so we try to merge these 3 points, organometallic chemistry, supramolecular chemistry, and luminescence, just combining our metal centers with a specific chromophore. So we tune the chromophores and we tune also the ancillary ligands. And these 3 parts of the molecules, the ancillary ligand, the metal center, and the chromophore, are responsible for the supramolecular assemblies, but also for the luminescent properties. So it is well known, at least for those working more in organic chemistry, that there are several types of weak interactions like hydrogen bonding, pi-pi stacking, other type of weak interactions that are very well known. But in these metals, in these gold and platinum systems, there are additional weak interactions that are not so well known, let's say, for people that are not working with them, that are metal-metal interactions, or what are called metallophilic interactions. These interactions play also a key role in our properties, on the properties that we are looking for. Okay, so let's say that with these general chemical structures, we play with the aggregation, supramolecular chemistry, in order to tune the resulting morphology and playing with the resulting luminescence and the colors, looking for specific properties. And I will show you today some of these. So how can we proceed? How can we make this self-assembly, this aggregation, and some examples on some of the applications that we are working. I would like to say that when we started with this, it was a little bit of serendipity. So we found that very simple molecules make self-assembly, giving rise to hydroxylators. And after that, we are moving more to a rational design. So I will show you a little bit the progress. First of all, just for those that are not so used to these gold and platinum metal-metal interactions, I would like to show you what are these metallophilic interactions. Okay, so as I said, these normal weak interactions that happens in organic systems, for example, hydrogen bondings are very well known, mainly those that are making this double strand of the DNA is very well known. Also, pi-pi interactions are very well known, but what happens with metallophilic interactions? So what we need is the two metals that display this closed shell configuration, like gold one, that is D10. And when they are approaching to each other, it arrives to a moment that they feel better together, let's say, establishing this metallophilic contact that is so strong, more or less with a strength comparable to a hydrogen bond. So this is very important for the resulting properties. And one of the founders or the person that defined it, it was Humbert Schmidt-Bauer, that it's now 90, and I'm very proud that I was with him 2 years ago when I was visiting professor at the University of Munich. And well, he's still active, so let's say that 90 years talking about, well, 90 years talking about metallophilic interactions not, but maybe 70 years. And well, he's a very nice, interesting conversation with him. So let's say that with these metallophilic interactions, what we need is that the metal should be at an adequate distance. And then we can construct a wide variety of different structures like those here presented that can display, as I said, different colors and different luminescence. So how can we know that these metallophilic interactions are present? So both in solid state or in solution. Let's say that in solid state, it's quite straightforward. So if we are lucky and we can grow single crystals suitable for X-ray diffraction, then it's just going to the diffractometer, and the experts on the crystallographers make some magician, and at the end we have the picture of our molecule. So this is more or less what we see. We see the crystal and we see the picture. But this is more or less a direct indication. With this solid state, what we know is that we can measure the distance between the metal centers, and then we can see if these interactions are present or not. And it has been observed that they can construct different types of assemblies like dimers, trimers, polymers, and more complex structures. As I am working on photophysics also, so we can see, or we have seen, that in fact the presence of these metallophilic interactions play a key role on the resulting luminescent properties. So some years ago, we made a systematic study when in fact what we made is several compounds that are dinuclear since they contain two gold centers, exactly with the same chromophore, this pyridyl ethylene ligand, that these two gold centers are coordinated by a diphosphane. This diphosphane differed on the flexibility and the rigidity and also on the length chain. With all of them, we could grow single crystals, so we could measure the distance between the gold metal centers. And in all cases, what we observe, independently on the distance between the metal centers, that there are two emission bands. One that is a structurally resolved band that it has been ascribed to intraligand triplet emission, and another one that is broader, let's say in shape, that has been ascribed to an excimeric triplet emission. So these two bands can be, let's say, in different proportion, or even they can be hindered one below the other, but they are present in all cases. We can see that we can be close to 3 angstroms, but also at 8 or near 9 angstroms, there are these two bands present. So we cannot see a direct correlation between the presence of a broadening band with the presence or the absence of aurophilic interactions. But what we could see is that, in fact, there is a direct correlation between the radiative processes. So if we measure the emission quantum yields and the lifetimes, we can calculate the radiative and non-radiative rate constants. And with this, we can observe that the radiative rate constants increases 2 orders of magnitude when we go from near 9 angstroms to near 3 angstroms, while the non-radiative rate constant, the variation is much lower. So the direct correlation is that the aurophilic contacts may more favor this radiative emission. Okay, so this is in solid state. What happens in solution? Well, in solution, we also made a systematic study with similar compounds with this pyridyl ethinyl chromophore, and this was made in collaboration with João Carlos Lima, the Nova University of Lisbon. So in this case, we perform absorption spectra of the compounds. So this is the absorption spectrum of this compound that presents also this vibronically structured band, that it is due to the pyridyl ethinyl chromophore. What happens if we have the same chromophore, the pyridyl ethinyl, but linked by a diphosphane? And if we see that these two chromophores are close to each other and connected through aurophilic interactions. So what we observe in solution is that the absorption spectrum is completely different. So this vibronically structured band disappears and the shape becomes broader. And this has been ascribed directly to the establishment of pi-pi interactions between the chromophores thanks to the coordination between the metal centers. And we could see that in all cases that aurophilic interactions are present. So we can detect by just recording an absorption spectrum if we have or not aurophilic interactions in our system. So is it a requirement having a dinuclear compound just to see if we have these aurophilic interactions? Well, the answer is no. So we can have also a mononuclear compound, but they can also be favored the presence of intermolecular aurophilic contacts if we put the molecule in a solvent that tends to aggregate a little bit. So this is a case of this molecule that, in fact, in dichloromethane, it was the absorption spectrum that I previously showed, but if the molecule is in acetonitrile, it tends to aggregate since it is not so comfortable. The molecule is hydrophobic. Acetonitrile is it's more polar, let's say. And in these cases, it tends to aggregate, giving rise to the formation of these aurophilic contacts. And we can predict that always that we can find this broad band that it's weak on intensity, but it's broad above 300 nanometers, it is directly correlated by the presence of aurophilic contacts. And in collaboration with Ramon Crauet, that made some calculations, we can ascribe that this band is related to this transition, supporting the presence of these aurophilic contacts. Okay, so what about the photophysics of aurophilic interactions? I explained you what happened in solid state. Can we translate the same results in solution? Well, we have some differences about what we observe in solution. In this case, more recently, we also performed a systematic study with different diphosphene or dinuclear compounds with a chromophore. And these dinuclear compounds are connected by a diphosphene that also differ on the flexibility as we can observe here in these four cases. In these cases, we could also grow single crystals suitable for X-ray diffraction in all cases, and we can observe clear differences. So we can see that, well, the more flexible diphosphene is this one, where the chromophores are, let's say, in a head-to-tail conformation, so they are not looking to each other. There is not possibility of establishing aurophilic interactions, at least in an intramolecular way. But instead, if we modify a little bit the diphosphene and closing a little bit by this ring, we can observe that these two arms are more closer to each other, although not enough to establish aurophilic contacts. But we can close a little bit more this diphosphene, and in this case, with this this bridging ligand that is called Schanfors, the diphosphane, we can enhance this approaching between the metal centers. And in this case, we do have the presence of these aurophilic interactions. And also happens the same in this case with the diphenyl phosphane bridging ligand, as we can observe here. I would like to say that, well, here we do not have any type of aurophilic contacts. Here we have intramolecular aurophilic interactions. And here, what we observe is that there are aurophilic interactions, but between molecules in an intermolecular way. Okay, so this is the difference. And we could observe that, in fact, these interactions are stable in solution. Okay, the differences in the luminescent properties are not so straightforward like in the solid state. In the solid state, we can have a direct correlation between the distance between the metal centers, independently if it happens in an inter or intramolecular way. Here, it is not the same if we have intermolecular contacts or intramolecular contacts. And what we observed is that, in fact, the higher emission quantum yields happen when we have intermolecular interactions, while the presence of intramolecular interactions favors the non-radiative processes and decreases the emission quantum yields. Okay? So this happens, or we could observe this with two series of compounds. It should be interested to be able to extrapolate, or if it is, if we can extrapolate this behavior, let's say, to other type and making a general statement. But at least for these two series of compounds, we can observe this difference on the quantum yields depending on if we have intra or intermolecular contacts. Okay, I would like to explain you a little bit about the aggregation with our compounds. So as I explained you before, some of the results that we started with this was a little bit of serendipity. In these cases, we synthesized these simple molecules that contains exactly the same chromophore as I was explaining now, but with these phosphanes. And these phosphanes are soluble in water. So we wanted to see if the presence of these water-soluble phosphanes can induce the solubility of the systems in this polar media. But what we observe is that they self-assemble, giving rise to these hydrogelators, giving rise to the formation of these very long fibers that are also emissive. So we were not expecting the formation of these weak interactions in so strong way, let's say, an extent way. But this is what happens, and also it can be extended, changing also the chromophore. So instead of a pyridyl, you will have a coumarin. It happens the same. We have these very long fibers, but we can make also other modifications, not only modifying the chromophore, but we can also introduce positive or negative charges in the molecule. So, well, sorry, in these cases, we could confirm the presence of aurophilic interactions thanks to the X-ray crystal structure. So as I said, if we introduce a positive charge in the molecule, what we observe is a radical change on the supramolecular assemblies. So we can introduce a positive charge here, this nitrogen atom of the phosphane, or at the nitrogen atom of the pyridyl group. And in these cases, we can observe that instead of these very long fibers, what we have is the formation of some vesicles, square-like structures, or some rod structures. So it is really relevant, not only the structure, but also if they are neutral or if they have a positive charge in any place of the molecule, modifying the resulting morphologies. Okay, but this, as I said, was a little bit of serendipity. So I don't know if it is your case, but at least in our case, we feel more comfortable if we can have some control or we can design what we want to happen in the lab. So we decided that maybe a rational design could feel us a little bit more comfortable. So we decided to move to self-assembly, but in a more rational control. And in this case, Andrea synthesized this compound containing this polyethylene glycol chain that is coordinated to the metal center through a pyridyl. And at the second coordination position, she introduced these chromophores that can be an ethinyl aniline or a propargyl coumarin. And we played with the self-assembly in order to construct complex structures like those here presented. So apart from the synthesis of this sample, what we wanted to see is the effect of the ligands of this self-assembly. So Andrea also synthesized some parent compounds having these water-soluble phosphanes instead of the pyridyl polyethylene glycol ligand. But what she observed is that having these compounds with ethinyl aniline, the compounds do not aggregate and even in some cases decompose. when we have the coumarin, but also with the phosphanes, the molecules were stable, but they also do not aggregate. So it is necessary the presence of this pyridyl polyethylene glycol for the resulting supramolecular assembly. So how can we perform these self-assembly experiments? Well, what we do is preparing a batch of different samples, exactly with the same concentration, but modifying the solvents that are present. So we work with two solvents. One of the solvents we call good solvent, where the molecule is completely solubilized. And another one is what we call a bad solvent, that say that it's the solvent that is promoting the aggregation process. So in these cases, we work with acetonitrile as good solvent and water as bad solvent. So what we perform are absorption and emission spectra and observe what happens. And what we observe is that, in fact, when we increase the water contents, the contents of the bad solvent, the absorption band, this is the absorption of the coumarin, of this part of the molecule. The absorption of the coumarin is decreasing on intensity, and at the same time, there is the baseline that is increasing. And this is directly correlated to the formation of some small aggregates. Okay, the information that we retrieved from emission spectra was also complementary, since what we observed is that when we increase the amount of water, there is the presence of a new band at longer wavelength that can be correlated to the formation of some pi-pi stacking between the coumarin units. So there is a complementary formation that, in fact, we have some excimer of the coumarin that are making these aggregation processes. So we know through these experiments that our molecule aggregates, but in fact we don't know exactly what type of aggregates we have. So we can have some micelles, we can have some vesicles, we can have some lamellar aggregates, so we don't know what we have. And we required other techniques, for example, DLS, dynamic-like scattering, that verifies also the presence of some spherical aggregates. And also we went to the synchrotron and we can perform some small angle X-ray scattering that both confirm the formation of these spherical aggregates. This was also confirmed by microscopy. So obviously microscopy is very nice to really know what is the shape of our samples. So both by optical scanning electron microscopy, but also by cryothem, since this indicates that in solution we still have these self-assembled spherical structures. Okay, so we could characterize through a wide variety of different techniques the formation of our aggregates, their supramolecular assemblies, their shape and size. But at that time, we arrived to a paper that it was not so new, but it, let's say, illuminated us, because we thought that it could be interesting also to know how many molecules are present in these aggregates. So it was a little bit tricky to understand between a lot of equations that, that were present in that paper, but at the end, once you understand, it is quite easy. Okay, so the procedure is just trying to stain our sample, the aggregates. We used pyren, and this can be, our samples can be stained in a blue color, let's say, as here presented, and then introduce increasing amounts of a quencher, that is this, so we introduce this, the CPC, making the emission of the compound decreasing on the intensity. So what we have to plot is, so this is how the emission of the pyren is decreasing on intensity, but not the emission of the coumarin. So the molecule is stable, the pi-pi sticking is stable, but this is just the probe that is decreasing is being quenched. And this can be directly correlated by this equation, the difference on the intensities, and from here we can calculate the number of molecules that are present in the aggregates. That in our cases was around 80 molecules in our sample, so it was quite big. Finally, just to know a little bit about, or to predict what type of interactions are present in this large assembly, we went to a collaborator at the University of the Balearic Islands, Tony Frontera, and he made some calculations that could well perform different type of assemblies between the molecules, and it seems that the most stable one is this pi-pi stacking between the coumarins a little bit shifted. But confirmed also that these 80 molecules confirm the sizes that we could record in the other techniques. So this is a little bit of overview of all the techniques that we can use from the beginning to the end to detect and determine the structure of our supramolecular assemblies. So let's say that playing with weak interactions, we can modify the shapes, the morphology, and the colors of our systems more or less as we want, with the normal surprises that we find in the lab always as we are working. And I wanted to explain you a little bit some of the applications that we make with our system. So the first application that we work is on the design of luminescent materials, mainly room temperature phosphorescence, more focused in the last years in the near IR. Okay, so we know that when we have our molecules, it can be excited to the singlet excited state, and it can go back to the ground state emitting light. This is fluorescence. But if we have a heavy metal or a heavy atom, it can be favored this transfer, what is called the intersystem crossing, through the singlet excited state to the triplet excited state. This is what is called the heavy metal effect. So with this heavy metal effect, this intersystem crossing, we can have, for example, phosphorescence when the electrons go to the ground state emitting light. Okay. And this is what we use. This is one of the reasons that gold and platinum are relevant for this population, favoring the population of the triplet excited state. And we are interested in that since they can have several applications in some different areas, like those here presented. In some of them, we are working, let's say, more autonomous, and others in collaboration with experts in the field. So some examples, just to know a little, to show you a little bit what are the modifications that we can observe. So for example, this is the work that was performed by Terafeli. She synthesized two series of compounds having exactly the same chromophore, coordinated directly to the metal center, and they are mononuclear or dinuclear. Again, we modify the phosphane, so we can have these mononuclear phosphanes, mononuclear compounds with these monophosphanes, or dinuclear compounds with these diphosphanes. In these cases, we can also vary the interactions that are present in the media. If we go to the emission spectra, what we observe is that, in fact, we can have different patterns. In one case, if we perform the emission spectra of just the chromophore, just the organic part of the molecule, we can observe that there is a fluorescence of the phenanthroid. So this is the the black line here presented. But what happens if this chromophore is directly coordinated to the metal center? So what we can observe is that, in fact, this intersystem crossing is favored, and we can have this room temperature phosphorescence emission. So this is reflected here in the emission spectra, since this one is decreasing on intensity, and what we have is mainly this band at longer wavelengths, that it is due to the phosphorescence. So we can play with the luminescence just by introduction of a heavy metal in the chemical structure. We also performed these studies with two families of compounds, having the chromophore directly coordinated to the metal center, or just with a chromophore with an alkynyl bond in between the metal center and the chromophore. In these cases, we not only recorded the emission spectra in solution, but also in the solid state by the development of some materials with this PMMA, polymethyl methacrylate, and Zionex polymeric matrix. And we can observe that we can obtain these luminescent materials with the compounds. What are the differences between these two series of compounds? Well, the difference is that, in fact, in the first series of compounds, we can observe that there is fluorescence plus phosphorescence. So this is what is called dual emission, because we can have the emission coming from two places, the fluorescence and the phosphorescence. While in the second case, we have that the only part of the molecule that displays fluorescence is the chromophore alone, without the coordination to the metal center. And we have pure room temperature phosphorescence, increasing also the quantum yields in 4 times, let's say, the quantum yields of the phosphorescence emission. So what is the reason of the increase of this room temperature phosphorescence? Well, we could grow single crystals in all cases also. And what we can observe is that there are some supramolecular assemblies that are induced by pi-pi stacking, CH-pi interactions, and gold-pi interactions. So the supramolecular assemblies seem the same in both families of compounds. So the only reason that can be the responsible of this enhancement of the room temperature phosphorescence should be the proximity of the chromophore to the metal center. When we remove the alkynyl bond, when the chromophore is directly coordinated to the metal center, there is a clear enhancement of the room temperature phosphorescence. So this was with gold, but I have also selected an example with platinum. So this was the work by Ariana. So in these cases, having room temperature phosphorescence is much easier. And in these cases, she synthesized these compounds with an NCN ancillary ligand, also with different chromophores at the 4th position. She could also grow single crystals that indicate the formation of some pi-pi stacking and also metal-metal interactions. And in all cases, we can have room temperature phosphorescence, pure room temperature phosphorescence with an emission quantum yields up to 60%, so quite good. So in these cases, we thought that as we already have room temperature phosphorescence, we can play with the colors. So let's induce aggregation with this mix of solvents, as I explained you before. So in these cases, we also use acetonitrile and water. And what we observe is that increasing the water contents, the proximity between the molecules induces a change of the color, as we can clearly observe in this image here. So also it is reflected in the corresponding luminescence spectra, where a new band at longer wavelength appears when we increase the amount of water. So this is what it is reflected in these samples above. Obviously, the last step of the aggregation is the solid state, when we have even a longer wavelength in the emission with this orange but close to the near IR emissive color. But we can also induce tuning on the luminescence, not only playing by solvents, we can also induce the proximity between the individual molecules by making some heterometallic compounds. So in these cases, what Ariana made is putting in contact this platinum, a solution of this platinum compound with a silver salt, and we can directly observe by naked eye a change of the color from this yellow-green emission to this orange color. And this is due to the formation of this heterometallic system that making the platinum centers to be closer to each other. This was also observed at the corresponding emission spectra with the presence of this new band at longer wavelengths for the heterometallic systems. At that moment, we started a collaboration with Professor Fernando Diaz at the Durham University. They are expert on the formation of OLEDs. So Ari went to Durham and was there 3 months to learn or to try to apply our systems in the development of OLEDs. And with this compound, what we observed is an heterometallic compound with this phenanthrene here at the 4th position. We can develop some OLED materials with a luminance and with a quantum yield of the luminance quite, let's say, moderate, but it should be said that in fact this value, that although it seems small, it is in the same range that the other previously reported by iridium compounds, that are those more explored in this field and are much expensive. So we can arrive to the same values, but with a less expensive material. Okay, so another field that can tune also phosphorescence emission is co-crystallization. And in fact, we are just starting on that, but well, we enjoy it, and I think that we will explore more on this field since it seems quite promising. So co-crystallization seems, let's say, from experimental point of view, not very difficult. It's just mixing a solution of one component with another component and see, well, what happens if they can make a co-crystal or not. So it seems, let's say, relatively easy, but maybe you don't have any results, so maybe it's not so straightforward at the end. But what we wanted to correlate is the effect of the heavy atom and the intersystem crossing in the resulting luminescent properties. And this was an idea that suggested, again, our collaborator in the Balearic Islands, Tony Frontera, since they have expertise on this field. So what we made is making react 3 of our compounds with a guest, let's say, with the iode pentafluorophenyl, and see what happens. So we don't know how can be self-assembled the compounds, if they react or not. So thanks to the X-ray crystal diffraction, we could know that in fact the 2 first compounds have this direct platinum iodine bond, weak bond interaction in both cases, while in the 3rd compound there is just pi-pi stacking between the platinum compound and the gas. So there are some clear difference in the resulting packing. How is affecting this in resulting luminescence? Well, this is what we explored. So what we make like a titration, we add increasing amounts of the gas to a solution of the host, of the platinum sample. And what we observe is that in the cases having this direct platinum iodine bond, there is a clear enhancement just by 0.1 equivalent of the gas in the solution. So there is a clear enhancement that is affecting, is improving the emission quantum yields. And this is due to an increase of the radiative rate contents in 1 order of magnitude. And this is what we called the double heavy atom effect, since we have one heavy atom, that is the platinum in our molecule, and a second heavy atom, that is the iodine in the gas, that is affecting the resulting luminescent properties. On the contrary, when we have these pi-pi interactions, but there is no platinum iodine bond, the differences in the emission spectra are really small. So this double heavy atom effect cannot be directly ascribed. We require the direct coordination between the platinum center and the iodine. And we think that, in fact, it should be further explored, since the combination of co-crystallization and double heavy atom can be really interesting for us in this self-assembly and luminescence. Okay, so let's move to the second application that I wanted to show you, is that the production of singlet oxygen. We have also focused in the last years on this field, since once we have populated the triplet excited state, not always we have the deactivation with a good radiative rate constant. Sometimes the molecules are not emissive. And this, one of the reasons that this can happen is because the electrons here can also react with oxygen, that in the ground state is a triplet, making some energy transfer and producing this very reactive species that is the singlet oxygen. Okay, so we are interested in that, since it can be applied to a wide variety of different applications, and we could establish the protocol in our requirement to detect the emission that is very weak. So it was not easy, but at the end we managed the emission of the singlet oxygen that is at 1,270 nanometers, more or less. So once we detect this weak emission band, it is a direct correlation that our molecule is producing this singlet oxygen. At that moment, when we started with that, there were only, as far as we know, 2 examples in the literature about these molecules, about gold complexes displaying singlet oxygen, that are these molecules here presented. So we thought that maybe it could be interesting trying to be a little bit involved in getting some results on this field. So our first contribution was taking these coumarin compounds with the phosphine that I previously shown, and with different substituents, so other different coumarins, and we could obtain singlet oxygen, although the quantum yields were not very high, up to 20%, let's say. So we needed more results. So then Andrea synthesized this fluorescein molecule with 2 gold phosphine units. She characterized the emission properties in solution, but also in different materials. In these cases, apart from Zeonex and PMMA, we went to polystyrene and cellulose. And first of all, from the photophysical point of view, we can observe that when our samples are in these matrices, display a quantum yield, an emission quantum yield that is much more favored than in the powder, let's say, in the solid state. So we are winning something, at least from photophysical point of view. But what happens regarding singlet oxygen? Well, we observed that all 3 molecules were quite good, minimum 50% of quantum yield on singlet oxygen production. So this was in solution, but as Andrea also synthesized these compounds, these organic matrices, we tried to measure the singlet oxygen also in the matrices. And what we observed is that, in fact, there is a clear winner, and this winner is the polystyrene. This polystyrene, so it was not a direct correlation between having a polar and an apolar matrix, because if not, we should have polystyrene and Zeonex in one side and cellulose and PMMA on the other side. So it was just the polystyrene. And again, in collaboration with Tony Frontera, he made some calculations, and we could know that, in fact, in the case of the polystyrene, this molecule presents weak interactions, but it is in the case where the fluorophore, the chromophore, is less in contact with the matrix, and for this, it seems that it can be more in contact, more easily in contact with the oxygen, making this singlet oxygen generation. So if this was right, maybe if instead of having these thin films, we can improve even the surface of contact with the oxygen, the singlet oxygen generation could be even enhanced. And in these cases, we synthesized these polystyrene microspheres. We can observe in these fluorescence microscopy images that the spheres were completely doped with our samples, since initially they are white, but in these cases they are displaying this yellow emission due to the presence of our compounds. And we measured singlet oxygen, and if this point here was this point here, now there is a clear enhancement just by increasing the surface of contact with the oxygen. Okay, this was with gold. We have also some examples with platinum. So in these cases, well, I would like to say that in fact, regarding this field, we are convinced that we need a kind of structure-activity relationship, since it doesn't seem to be a direct correlation that if I design this molecule, I will have a molecule with a really high singlet oxygen photogeneration. So we are focused in the last years on trying to have this structure-activity relationships, trying to modify a little bit the samples to get more information and at the end be able to predict how much or how much favor should be this singlet oxygen generation with a determined chemical structure. So in these cases, with these platinum tweezers, the theoretical calculation suggests that there are some platinum-pi and platinum-platinum interactions that are more favored with these R groups are less bulky, as expected, that are yielding room temperature phosphorescence that can be observed in this spectra. And this is due to the presence of this platinum center that is enhancing again the intersystem crossing. So we were previously convinced that in fact this part of the molecule, the platinum and ligand, should be the responsible of the singlet oxygen generation. But what we observed is that in fact, on the contrary, it seems that the linker plays a key role, since these values that are here highlighted are those containing this linker with two methylene groups between the phosphorus atoms. So it seems that on the contrary that we were expecting, in fact, the linker are playing the key role on the singlet oxygen generation. And this was directly correlated to an enhancement of the energy transfer constant that can be calculated, that this is the value with one methylene, with two methylene, and with a benzene, so clear higher in the case of the DPPB. So let's move to the very fast to last applications. One is the interface between supramolecular chemistry and nanomaterials. So I thought that being here at the ICMAB, I should talk a little bit on something on materials. So for this, I decided to put one of the examples. So first of all, remember that I explained that this molecule can give rise to the formation of some hydrogelators. When we introduce a positive charge of the molecule, in this case, we can have some kind of square-like structure and some kind of spherical vesicles when we change the counterion from a triflate to iodine. So these supramolecular assemblies based on organometallic compounds were put in contact with silver nanoparticles. And what we observed is that in the case of the fibers, we have this rod or wires based on gold zero. We can have some square-like morphologies based on gold zero or spherical gold zero assemblies. So it seems that the supramolecular assemblies are inducing to the shape of the resulting nanomaterial. Okay, so this was verified also by electron microscopy, as can be here observed, also by the corresponding EDX analysis, and also by corresponding TEM images, and of course by the UV visible, that indicating the presence of this gold zero. The second example of our work on materials was how can we affect these metallophilic interactions with nanomaterials. So what we made is making react a solution having our hydrogelators based on gold 1 assemblies, okay, with nanoparticles. And what we observed is that the solution with the nanoparticle disappeared, the color disappears immediately when it was in contact with our hydrogelators. So this was because the hydrogelators was making some gold gold interaction with the nanomaterials and transferring the nanoparticles to the aqueous phase. So this was an easy way to solubilize in water nanoparticles. So this work always done what we have in our nanomaterials, metal centers that can induce metal-metal interactions with our hydrogelator. So this was useful with gold nanoparticles, with silver nanoparticles, with a mixture of different nanoparticles having gold or silver at the surface. But for example, it doesn't work with iron oxide nanoparticles. But if we make a thin film of gold at the surface of the iron oxide nanoparticles, then the process works. So we need a gold center or a metal at the surface that can establish these metallophilic interactions, and then we can induce a fast solubilization in water of our samples. Okay, let's move to the last application. That is one selected application on sensing. So why these molecules are interesting on sensing? Well, because if we have some supramolecular assemblies, when they are in contact with a specific gas, these supramolecular assemblies can be destroyed or can be even more favored. And this induces some changes on the luminescent properties or on the morphologies, for example. So one of the examples that I wanted to show you here are that we are interested, thanks to that cost action that ICMAB explained, on the detection of some contaminants, for example, on polyaromatic hydrocarbons or perfluorinated compounds. So in these cases, what Araceli did was synthesizing this gold compound, having this pincer structure, and putting in contact with different contaminants, let's say. And the idea is trying to see if when the contaminant is within the tweezer, then it can induce some changes in the luminescent properties. So this is a sensor. And why it is important using luminescence? Because luminescence is very sensitive. So you can really detect very, very, very small amounts of samples. So this was the interest on this field. So we observed that in fact this process worked always that we have these extended polyaromatic compounds. It didn't work when we have these linear perfluorinated compounds. So there is an enhancement of the emission of our sample, and this is changes on the light that can be fitted to some association constants that are higher when we have a more extended aromatic surface, making this pi-pi stacking with our tweezer. This was in solution, but then we decided to make like a proof of concept, just introducing our materials in a matrix, in a polymer. So this was, in these cases, we chose cellulose because cellulose can be permeable to water. So the idea was if we have let's say the proof of concept, okay? So if we have an aqueous solution with a contaminant, if we have our material with a determined luminescence, in this case, yellow-green emission, if we dip our material in a contaminated sample, we can see if the sample is contaminated or not, because it produces a change on the luminescent colors. So this is really a simple idea, but it can be translated to really difficult places of people that is in a discotheque that they are offering you a glass of water, well, not of water, but you would like to see if there are some contaminants or not, so you dip and you say, maybe I will not drink it, okay? So if you are making these changes on the emission. Okay, with this I finish. So I hope that I could be clear enough to translate you the effects of supramolecular assemblies, that we can really, by modification of these weak interactions, we can produce different type of morphologies, that the presence of these heavy atoms are really important to populate the triplet excited state. And this is really relevant for different type of applications like those here presented today. So of course, I wanted to thank all the people that has been involved in this work. So mainly the people of my group, the collaborators, these are the most close collaborators in this work, but also others, also the funding, and thanks to all of you for your kind attention.
Thank you very much. Yes, you are time. It's very nice. Thank you very much for the nice overview of all the work that you are doing. I think to know a bit your expertise, and find possible synergies, it's been very, very nice. So now we are open for questions.
Thank you, Laura, for this very nice talk. So my question is related to the oxygen generation or oxygen production. In the first example, the gold complexes, you use different matrices. And I have two questions here. The first one is, which is the role of the matrices for the generation of oxygen singlet? And the second is a technical question. How do you do for the measurement of these complexes in the matrix? So
okay. Let's start for the second question. So just to introduce our compounds in the matrix, we have the matrices are, let's say, soluble or more or less soluble in dichloromethane or with a polar, well, we have to choose exactly the solvent where the matrix is more or less soluble. Then we introduce the desired amount of our compound, and then we make like a thin film and let them evaporate, and we can have the matrix. Okay. And the role on the singlet oxygen photogeneration, we really didn't know. For this, theoretical calculations help to suggest that maybe, so it seems that the compound should have some interaction with the matrix to be really stable there, let's say. But if it is, if the compound is too close to the matrix, it cannot be so easily in contact with oxygen. So it is decreasing the possibility to make this ROS effect.
thank you.
Okay.
Thanks very much, Laura. Sorry, I was late. I had a question about the complex that you have between the, I think it was platinum complex and the iodofluorobenzene.
The co-crystallization.
Yeah, right. So you showed that when you just add a small amount of the iodofluorobenzene, you have a big increase in phosphorescence.
Yes.
So why is that? Because that's not like a typical titration curve, right? It's very...
Yeah, it's super fast. At the end, when we plot, we can observe that there is really an exponential, but the first point is really fast. I was also super surprised with that, so I make the student to repeat, and it was reproducible. So it seems that just the first interaction between the iode or the gas, let's say, the iodine with some platinum centers, it is inducing this increase of the aggregation. So yeah, I agree with you that it's quite surprising, but it is reproducible also.
But what does it do? Does the iodobenzene generate a polymorphic structure of the aggregate or something? Or
I would say that just a small amount of this co-crystal it is making the responsible of this enhancement of the emission. But at the end, it arrives to a plot when you have the one-to-one.
Right. Did you look at the powder diffraction of the different samples?
Yeah, we have also some pi-pi interaction. So there is one molecule making some platinum iodine, but there is another iode pentafluorophenyl making some pi-pi stacking interaction with the molecule on the other side.
Okay, interesting. Thanks very much.
Thank you.
Thank you. I don't know. Is there some other question? Okay.
Thank you, Laura, for the presentation. With this slide you have here in front, have you made an application of this singlet oxygen to oxidize an organic compound and comparing with just the triplet oxygen under the same conditions?
We haven't done, so we are looking for that. So in fact, we are really interested in trying to make this as an application for photodegradation of contaminants, let's say. We are now trying to improve having the adequate photosensitizer introduced in a material and trying to find the adequate conditions to pass, let's say, some aqueous solutions through our material, irradiating, producing the singlet oxygen, and observe what happens at the end. But we haven't arrived to the...
But one of the problems that I guess you were going to face is that singlet oxygen, the lifetime of that is very, very short.
Yeah.
So
Yeah, for this, it should be in a continuous way. Yeah.
Okay, thank you.
Thanks to you.
Hi, thank you, Laura. You showed a graph at the beginning with the difference that makes the intermolecular interactions into the quantum yield.
Mm-hmm.
How would you experimentally drive the system into intermolecular interactions more than intra, right? If it's what you want to maximize the quantum yield. And yeah, just another question about the quantification that you made of the number of aggregates. I think it's a very interesting approach. I didn't know about that. So yeah, I was just wondering how reliable is that, considering that it's not a controlled way in which you produce the aggregate. So you mentioned 82 molecules. How dispersed is your system? Do you have an idea of the, how is the dispersity into that?
How is the dispersity on the value that we
I
can
mean, if
calculate?
you consider that all your aggregates are composed of 82 molecules.
Well, I think that the key point should be just looking at the size of the aggregates and the morphology through other techniques like TEM or cryo-TEM and observe if they are more or less homogeneous. So if all of them are more or less homogeneous, I think that we can expect that the average number is the one that we calculate. Obviously, if we have a clear dispersion, this cannot be so rigorous. Okay, this is the second question. Regarding the first question, I would say that if we would like to improve intermolecular interactions, we know that flexible diphosphanes are generally good on that. At least our experience is that this phosphane having 3 methylene groups between the phosphorus atoms, the DPPD, are, at least in all the systems that we have studied in the group, almost in all cases, they induce these intermolecular contacts. So we should have obviously a design where the chromophores are not close to each other. So you need some flexibility. In fact, we can destroy any type of autophilic interactions, either intra or inter, also with the bulkiness of the phosphane. So we have also some recent results on when we introduce really a bulky phosphane, there are no autophilic interactions, neither intra nor inter. So we need that the phosphane, it is not super big, but also some flexible.
Okay, I don't know if there is the last question. Otherwise, I think that we have to thank Laura for the nice conference.
Okay, thank you.